Okay, welcome everybody again for the seminar today. And today's speaker is Prabha Mandayam from IIT Madras. He is my colleague and also collaborator. And probably there is no better choice of a speaker for this topic today, which is about PETSmap. So she will introduce it in the context of open quantum systems, and now then she will also cover its application to understanding the bulk to boundary map in holography. So, and that's one of the most interesting contemporary topics. So over to her then. Over to you, Prabha, to tell us about all these exciting things.
Thanks, Ayan. Well, thanks for persisting with me and asking me to speak here. And Ayan has been trying to get me to speak here for a while now, but it's good that I finally made it. So the idea was to talk about this particular object called the PETSmap, which originally arose in the quantum information and quantum computing context. And has now become very important in this context of holography, this so-called ADS-CFT correspondence. So what I'll attempt to do is to first introduce the PETSmap, let's say the way I know and understand it, the way I use it, and we'll see how that then has implications for this holographic correspondence and how it's being used today. I must tell you that I think within the last year, say late 2019 to late 2020, there have been, I think, 5-6 papers maybe in Journal of High Energy Physics, mainly involving the PETSmap, right? So that's kind of how important it has become in this context of field theories and the gravity field theory duality, so to speak. Okay, so let me just give you the outline of my talk. By the way, I don't see anybody, so if there's any issue, please either type something in the chat or just interrupt me at any point, okay?
Yes. So people will interrupt you and ask questions in between. And if they can't,
yes,
they will
please.
Put in the chat box. I will just read out the question.
Sounds good. Yeah. I may also need some help from the dual mystery guys for the second half when we actually get into the duality stuff, right? Okay, so first I'll, of course, since this is going to be a mixed audience, I thought I will introduce briefly quantum error correction, and I will talk about the distinction between the so-called general purpose codes, which are somewhat already well known maybe in the broader physics community. They go by the name stabilizer codes often. And that idea probably, at least the folks from condensed matter know a little bit about that. And then I will contrast that to channel adapted codes, which is what I have been working on. And that is where the PETSmap naturally plays an important role. And then we'll move on to talking about, we'll actually move on to talking a little bit about information theory. So that's where the PETSmap enters. And this stuff I'll sort of try to cover quickly because I've also spoken about it in other talks recently. So maybe people already know about it, but I just thought that'll provide the context and the background to this. And then we'll move beyond standard quantum error correction, so to speak. And we will talk about these two important aspects. One is how the PETSmap plays a role in the context of quantum relative entropy. So I'll introduce the relative entropy, and I will talk about this question of monogamy of quantum relative entropy, its relation to something called strong subadditivity. So these are very fundamental questions in quantum information theory. And the name PETS that one uses with this certain map, right, actually comes from this Hungarian mathematician, or maybe I should say functional analyst, Daniel Petz, who actually introduced this in precisely this context of quantum relative entropy and strong subadditivity, right? And then I will move on to talking about how it naturally becomes a universal recovery map in the context of holography, okay? All right, so this is just a standard introduction to error correction from a very, very materialistic point of view today, that we have these noisy intermediate scale quantum devices, various companies promising 50 to 100 qubits, but they're all noisy. So quantum error correction is our basis for thinking that quantum computers can actually be made robust and scalable, right? So what is this noise? Why are these qubits noisy? Well, because you have this sort of cartoon picture where you have the system and environment interacting via this unitary, which is USE is what I've called it here. And this system bath interaction or the system environment interaction, while that is unitary, if one is interested in how the system alone evolves, then that is no longer unitary. That is in fact modeled by what's called a quantum noise channel. And this has various names. It's called a quantum operation. It's called a quantum channel. It's called noise. And it is not a unitary map. It's not a unitary transform from rho to E of rho. Rather, E is a different kind of dynamical map. So this is what we call a completely positive trace preserving map, right? And one way to see how this arises is to say that your system and environment initially started out in what's called a product state. This tensor product sign here means that they were not initially correlated to begin with. I have not put in time explicitly here, but one can think of this as a map from rho s at time 0 to rho s at time t, rho s being the system density matrix. And this being the initial state of system and environment being in a product state where phi sub e denotes a fixed state of the environment. And then you allow system and baths to evolve together according to this interaction unitary, right? The unitary coming out of the interaction Hamiltonian, you call that U sub SE. This is the joint state of system and environment after a certain time has elapsed. And then you trace out the environment degrees of freedom, right? This is a partial trace over the environment. And when you do this, what you end up with is a map purely from system states to system states. You can think of this as a map from rho s at time 0 to rho s at a different time t, right? And this map will not be unitary in general. So it will be unitary, say, only if the environment is a single degree of freedom, right? So this, so this in general will be what's called a completely positive trace preserving map. So this is what I'm going to abbreviate and call as CPTP map from here on, right? It's completely positive means that it maps, not only does it map positive operators to positive operators, any extension of the map is also positive. Trace preserving means, of course, that it preserves the trace. Both of these properties are important to ensure that it is a map from density operators to density operators. And so this CPTP map is a well-studied object in the mathematical literature. It turns out that if a map on a set of operators, on a set of positive operators, which is what density operators are, if a map on a set of positive operators is completely positive, then it can always be decomposed. It can always be represented by some set of operators, which we today call Krauss operators. So these are denoted as E sub I, so that the action of the map can be described succinctly via this kind of an operator sum representation, right? So the action of the map on the density matrix is simply written as sum over I, EI rho, EI dagger. The fact that the map is trace preserving then puts a condition on the EIs. Otherwise, there's no other condition on these operators EI. They could be any kind of operators. Of course, operators from the set of bounded linear operators on the Hilbert space, right? But they are not Hermitian, they're not necessarily unitary, etc. But they have to satisfy this completeness relation for the map to be trace preserving. Sum over I, EI dagger, EI is identity, right? So this is what will characterize a quantum channel for us, because this represents the non-unitary evolution which tends to decohere the quantum state, right? There's a loss of coherence because this evolution is non-unitary. And this is what we will call a quantum channel. So a simple physical example is this Jaynes-Cummings interaction, where
Prabha,
you have a tool.
Prabha, sorry to interrupt. I just wanted to understand from here, what is the actual difference between completely positive and positive? And what exactly it is, how this expression changes if it is positive and not completely positive.
Okay, how does it change? So for a positive map, first of all, this property does not hold, that you can have such an operator sum decomposition. As far as I know, that's I think that is correct, that statement. So what's the difference, right? So E of rho, of course, once you write it in this form, right, you see that this form also is positive, right? So rho is positive, right? Rho is a density operator. So I can write this, for example, as EI square root rho times EI dagger, right? So then I can write this essentially as a sum of positive operators, right? And this is the final state after the action of the map. So this ensures, this operator sum representation ensures that the map is positive, in the sense it maps positive operators to positive operators. But it also ensures that the map is completely positive. Completely positive means that if I take any arbitrary extension of the map, so imagine that this rho, this system state itself, was entangled with some other ancillary system, right? I'm not talking about the environment here, but imagine that it was maybe entangled with some other ancillary system, right? But nonetheless, the system continues to evolve via this interaction with the bath, right? So what is then the joint state of the system and ancilla? That would be described by, and let's say that ancilla is some kind of, fixed state, like, it's not something that is evolving, or maybe it's evolving according to some other map or whatever. But this E acting on system tensor, any extension, right, acting on such an entangled state should also be positive, right? So a simple example of a map which satisfies positivity but not complete positivity is the transpose map, right? So imagine you just consider the map rho going to rho transpose, right? Now that map preserves positivity, but when I take an entangled state and I do a transpose on only one half of it, one subsystem of it, and not on the other subsystem, then that's of course a famous partial transpose, right? Which can, and if the state is entangled, then at least for 2x2 and 2x3 systems, you know that it will necessarily give you a state which has negative eigenvalues.
Sure, okay.
Right, so that's a classic example of a positive but not completely positive map. In fact, such maps are typically considered entanglement witnesses for this reason, right? So this complete positivity ensures that the map is physical to any order. It's physical, any extension of the map is physical, right? I hope that answers your question.
Yeah, it does.
Yeah.
It does. Yeah, thank you.
Okay.
Thank you. Okay.
Sure.
I have a question, a simple question. So is this map that you have written here, E rho is equal to EI rho EI, is this applicable to operator other than rho?
Yeah, indeed. The idea is that every state of the system will evolve according to this. So once you fix the interaction unitary for me, which is this USE, right? Then every system state evolves according to this map. And that's why it's a map, right? It's a map from all states on this system Hilbert space to a space that is isomorphic to it, which could be the system Hilbert space at a system at a later time or whatever, right? Physically, it would represent system at a later time. That's all.
I see. So,
right.
In particular, it will imply that any operator will just follow this, as well as multiple operators, like correlation function of operator will also follow this. Is there any such statement?
If you are trying to follow the evolution of the correlation function, the correlation function is some kind of scalar. It's a functional on the density operator, right? Typically, like you will take some kind of expectation value or a trace, or with an OTOC, you take trace of the state at two different times or something like that. So at any point you want to write down rho of t, then this kind of a map will capture that rho of t for you, right? Going from rho at time 0 to rho at time t. So this is a map on the space of operators, right? So scalar functionals will accordingly change, right?
Okay.
Does that answer your question?
Yeah, okay, thank you.
Sure. Okay,
But here, here, Prabha, you are in the Heisenberg picture, I guess, right? I mean, this is where this state is evolving, the operators are not. But anyway, this is just simply you're mapping the density, you're evolving the density matrix, not the operators.
Correct,
Anyway.
correct. I'm not yet talking about, no. I'm not talking about, say, the evolution of the algebra of operators on the space or something. No, I'm talking about states in the sense of density operators. Yeah, indeed. So I'm not yet in a Heisenberg kind of picture. Actually, in a Heisenberg picture, which is kind of dual to this, right, you will in fact find that the dual of this map E is what will capture the evolution, right? So for example, in this holographic context, when you in fact need to go to the Heisenberg picture, that is what you do. It's exactly the dual of this map.
That's yeah. So in the holographic case, you consider the dual of this E row map, exactly. Yes.
Correct. Yeah. And more often than not, the dual can be thought of as the adjoint, but one has to be careful in that thing. We'll come to that later. So, okay, maybe I should say that right away here, that the adjoint map of a given CPTP map need not be a valid physical map always, right? It need not be completely positive. Sorry, actually, I'm saying the other way around. It will be completely positive, but it need not be. I'm sorry. It'll of course be completely positive, but it may be trace increasing, right?
Ma'am, what do you mean by adjoint map?
Yeah, so adjoint map would mean that the Krauss operators are given by EI dagger instead of EI. So I said the Krauss operators here are given by the set of operators E subscript I, right? And then the evolution goes as EI row, EI dagger, and a sum over the I index. Now imagine a map with Krauss operators which are given by the adjoint of this map, right? Which is EI dagger. That's what I would call the adjoint channel, right? That's what is called E dagger, right? Now this adjoint channel has Krauss operators EI dagger, but while sum over I, EI dagger, EI is guaranteed to be identity, right? Because this map, the map that you started out with, is trace preserving. The adjoint map, which then requires that the sum EI dagger should also be identity. For the adjoint map to be trace preserving, do you see that? The sum over I, EI dagger must be identity. Okay? There are a special class of maps for which this holds, and those are called unital maps. Is the contrast clear? That if instead of EI, I pick the adjoints of these operators EI, right? Then my operator sum representation becomes EI dagger row EI, right? That's what the evolution will look like. Now, there is no guarantee for me that sum over I, EI dagger will be identity, but not, I mean, let alone identity, there's no guarantee that sum over I, EI dagger will be less than or equal to identity. So I should have put that condition somewhere actually. See, the physicality of the map requires that you may not always have a map which is trace preserving, right? But you can always normalize it to be trace preserving so long as it is trace non-increasing. But that is not guaranteed for you when you take the adjoint of a trace preserving or trace non-increasing map, because that tells you something about EI dagger EI being complete or being less than identity, but it does not tell you anything about EI dagger. So there's a special class of maps called unital maps for which this actually holds, where the adjoint is also a trace preserving map naturally. Okay. So let me proceed. So one physical example of this is what's called energy. This one physical example would be this two-level, any two-level system. It could be an atom in a two-level atom in a cavity sort of thing, where you have this, you have pretty much restricted the Hilbert space of your system to these two levels, and it is interacting with a radiation field, and it is interacting via this Jaynes-Cummings interaction. Then one can do this math where you take the Jaynes-Cummings Hamiltonian, you do the rotating wave approximation, you can truncate your environment. So the environment becomes the radiation field. The system is this qubit, right? This two-level system. And if you truncate the environment degrees of freedom to be within, in the Fogg basis, if you truncate it to the 0 and 1 states of the Fogg basis, right? So a 2-level environment, basically. Then you get a channel out of it, which is called the amplitude damping channel, right? And this channel essentially captures this idea that if the system is in the ground state, then it is unaffected. That is the ket 0 of my system, right? And that is unaffected. But if my system is in the excited state, then there is a certain probability with which it will decay down to the ground state. But this then happens with the emission of a photon. And that's why I restrict my environment degrees of freedom to just the vacuum and the single photon state. Then I have a channel of this form with just 2 Krauss operators. One which captures the fact that the system in the ground state is left unaffected, and the other which captures the transition from the excited state to the ground state. That is what this off-diagonal operator does. It takes a ket 1 of the system and takes it to a ket 0, which is a ground state with a probability gamma, right? Okay, so this was just an example of this picture of CPTP maps. One can, of course, go ahead and check that E0 dagger E0 plus E1 dagger E1 is identity. In fact, you can check that this map is not unital, which means E0 E0 dagger plus E1 E1 dagger is not identity, right? And so the adjoint of this map is actually not a trace non-increasing map, okay? All right.
Sorry, just one quick clarification. How is the dagger defined in this case? What do you mean by the dagger of the operators here?
It's a complex conjugate transpose.
But for finite
transpose
2x2 matrices, for finite 2x2 matrices, if you define dagger that way, doesn't it always satisfy? Meaning, won't it be both ways? EI dagger EI equal to identity as well as EI dagger equal to identity?
No, not necessary. You see, the dagger of this becomes the 1-0 operator. No?
Sorry. This is not both the entries are not there. It is only upper triangular, I said.
This E1 is like that, but in general, that may not be true.
So your scalar products are the standard one. 0, 0 is, 0, 1 is 0 and 1, 1 is 1 and 0, 0 is 1. Right?
Correct. Yeah.
Thank you.
Yeah, sure. Okay, so one can now study somewhat simpler channels or maybe nicer channels. And this is the class of Pauli noise channels. What one means by Pauli noise channels are those channels whose Krauss operators are exactly one of the Pauli operators, right? And this forms a very important class of channels because, well, that any 2 cross 2 matrix can be written as a linear combination of the Paulis, right? And since most of, we are working with linear systems, so the fact that the Pauli operators form a basis, right, makes the class of Pauli noise channels an important class to study, right? So here's an example of a Pauli noise channel. This is what's called the bit flip channel. And the idea is that this ket 0 could get flipped to ket 1 with some probability p, and it remains 0 with probability 1 minus p. So now you see this decoherence coming into play, that you start with a pure state, let's say ket 0, right? But then under the action of this map, you will actually decohere into a mixed state. Because with some probability, the state remains a 0, 1 minus p, but with probability p, the state actually becomes a 1. So the final state is actually a mixed state. It's a convex combination of this form of 0 and 1, right? And you can, of course, see that this is nothing but 1 minus p identity acting on 0, 0 identity, plus p times sigma x acting on 0, 0 sigma x. So you can sort of read off the Krauss operators of this map like this. So this term corresponds to the identity Krauss operator, and this term corresponds to the sigma x Krauss operator, right? So here's a map whose Krauss operators are essentially identity and sigma x, or rather they're proportional to identity and sigma x being the standard Pauli x operator. So here you go. The Krauss operators for this channel are of this form. Square root 1 minus p identity. Remember, it acts by conjugation, right? So it's square root 1 minus p identity and square root p sigma x. Now, this is very unlike the example I showed you of the Jaynes-Cummings model and the amplitude damping. That is a non-Pauli channel, right? This is what I would call a non-Pauli channel. because this operator, if I write it out in matrix form, is just 1, 0, 0, square root 1 minus gamma. And this is, like someone just pointed out, is an upper triangle matrix with 0, square root gamma 0, 0. And neither of these are scaled Pauli operators. Of course, you can write E0 as a combination of identity and sigma z. You can write E1 as a combination of sigma x and sigma y, but they are not per se Pauli operators, right? So you will see that there's a distinction between this class of channels. For one thing, you can note already that these Pauli channels are actually unital channels, since I already mentioned this unitality business, because the Krauss operators, which are identity and sigma x, are actually unitary operators, right? So sigma x dagger is identity, I dagger is identity, no matter which way you do the adjoint on this. And so when you sum it up probabilistically, you always get identity. So these are indeed unital channels. All Pauli channels are unital channels. And to just show the time explicitly, typically this probability of the bit flip goes as an exponent, right? So the idea is that t is equal to 0, the probability of the bit flip is 0. And then this is sort of exponentially growing from 0 to half, right? As t starts from 0 and goes off to very long time. So in the long time limit, you are in a maximally mixed state, right? Under the action of this kind of a map. And this time constant is what we call the coherence time, right? Similar channel is a phase flip channel where the Krauss operators could be identity and sigma z instead of identity and sigma x. Then, of course, I could add sigma y to the mix, and I get what is called a depolarizing channel, which has an equiprobable mix of all three Pauli operators, right? So the Krauss operators in this case are x, y, z, and identity, right? And this is one form of, this is not the most general Pauli channel. The most general Pauli channel would not have equal probabilities here, but this is a sort of nice symmetric Pauli channel, right, which has equal noise along x, y, and z, right? Okay. So now we enter the domain of quantum error correction, having hopefully I've explained the noise structure to you. So now that you know that the system is undergoing this kind of an evolution via a CPTP map, let's say you know what the Krauss operators are, can you then recover the state back, right? So the idea is your state has decohered in this fashion. You started out what was a ket 0 has now become an incoherent mixture of 0 and 1. So is it possible, let's say after a certain time, so there's a certain p value, the p parameterizes the noise. So after a certain time, is it possible for me to recover the initial state? Of course, this is a non-unitary evolution, so you cannot exactly get back the state. You cannot reverse the dynamics exactly, but can one do it well enough, right? And that's where error correction comes in. And the way to do it, this is just a nice, so these are the last two lines of the QEC sonnet. If you like it, I encourage you to go and read up. If you just Google Daniel Gottesman QEC sonnet, you should get the entire poem, right? It's a nice take on limerick on quantum error correction. So the idea is that you have to now introduce some redundancy, right? If you really want to be able to reverse the action of such a CPTP map, a non-unitary map, then you have to introduce some redundancy so that this information about the action of the noise is in some sense spread out to a larger Hilbert space. And then you can do some clever tricks and get back the state that you started with. So what do I mean by that? So let's say I started out with alpha 0 plus beta 1, which is some coherent superposition of 0 and 1, right? Now, instead of working with alpha 0 plus beta 1, it might help for a noisy system to rather work with alpha 0, 0, 0 plus beta 1, 1, 1. Note that this is not 3 copies of alpha 0 plus beta 1, right? Now, that cannot be done. You cannot make copies of an arbitrary quantum state, right? That's the essence of the no cloning theorem. So you need to find an encoding process, a way to introduce this redundancy in a way that circumvents the no cloning theorem, right? So you go from alpha 0 plus beta 1 to a state like this, which is actually an entangled 3-qubit state. If alpha and beta were exactly 1 over square root 2, then this is what this would be what you know as a GHZ state, perhaps, right? So you need to find a way of doing this, and the way to do it is to use what are called ancillars. So that's the additional qubits, that's the additional systems that you need to add, and then you need to have unitaries that entangle this original system with the additional systems, right? So this is a circuit representation of this. I mean, you don't need to worry about this except to know that this ket 0 and ket 0 here, these two are the additional ancillars. This sort of symbol here, which is joining the first wire and the second wire, is basically entangling the first 2 qubits. It's a C0, what's called a C0 gate. This is another C0 gate between the second and the third qubits. Psi is the state which you wish to encode, right? That's an arbitrary single qubit state. So at the end of this encoding process, which is the first half of this circuit before this box which says error, what you have is a 3-qubit state which carries the same information which you had in the single qubit state, right? And you've done this in an isometric way. If you think of the operation on the 3-qubit Hilbert space, then you've actually done it in a unitary fashion. So the encoding is completely reversible, right? And that's what you want. You want a reversible way to encode the information because the error is irreversible, right, by itself. But now the error is acting not on a single qubit, but on 3 qubits. And then you take advantage of this fact that you have an entangled state, and then you do some clever measurements and decode, right? So you have gone from what are called physical qubits, right, to logical qubits. So this 3-qubit state is now my logical 0, and this 3-qubit 1 is my logical 1, right? And this is a terminology which you will often find being used in these, even in these ADS CFT papers, which talk about one part being the physical and the other part being the logical space, right? So that's what one means. One means that you've taken this information which was in a single ket and sort of encoded it in a logical space of 3 qubits, right? Okay, so now you make use of the fact that the noise is, okay, so I should have put in something here about the IID nature of the noise. You assume that this process is identical. So if I have 3 qubits, I have the same kind of bit flip noise acting on each qubit. That's what this error does. And it's identical and it's independently distributed. So the noise doesn't correlate, doesn't cause any correlations across these 3 qubits, right? It's independent bit flip noise on qubit 1, independent bit flip noise on qubit 2, and independent bit flip noise on qubit 3. So based on this assumption, you can then argue that you can distinguish between bit flips on these 3 different qubits. And then essentially what you're doing is a kind of parity check, or if you wish, a majority vote, right? So if you know that 000 under a single bit flip can only go to 100 or 010 or 001. Similarly, the 111 can only go to another set of 3 distinguishable states. So in all, you have 6 distinguishable states plus the 2 states that you started out with. So there are 8 distinguishable states, which is indeed, these are the states that span the 3-qubit Hilbert space. And so you have managed to find a distinguishable mapping of errors, right? And then your errors can be detected and corrected by appropriate measurements. So that's what the second half of this circuit is doing, okay? And one can show that such a process, the encoding and the decoding together, improves the coherence time of the qubit, provided this probability of the single qubit error is less than a half. Because if your because once p is greater than half, then the higher qubit errors become more likely, right? But then physically, you're never going to be in that kind of situation based on the time picture that I showed you, right? This is the most noisy state, is p is equal to a half, right? Okay. So let's now formalize this notion of encoding. So you've taken information from a D0 dimensional Hilbert space H0, and you've put it into a subspace of a larger Hilbert space. So in the previous slide, what I did was to take a 2-dimensional Hilbert space, which is a single qubit, and I encoded that into a two-dimensional subspace of a 3-qubit space, the larger Hilbert space, right? And this is an isometry, and if I think of it including the ancillars, then it's a unitary, right? And this S simply denotes states, right? So this is a map from states on what one would think of as a physical space to the code space. So the C is what I call the code space. So in the previous slide, the code space is nothing but the span of these two states, right? It's a pair of orthogonal states which correspond to my logical 0 and logical 1. The span of this is the code space. It's a two-dimensional subspace of the larger space, which is a 3-qubit space, which is an 8-dimensional space, right? Okay. So that's what this is saying, is a subspace of the set of states on a larger Hilbert space. And then you need to have, so this is what an error correction procedure involves. It involves an encoding. It involves encoding into a code space. And then it involves a certain recovery procedure, right? The recovery, the way I presented it here, seemed to be some kind of measurement, right? Basically, I said you can distinguish between the error acting on different qubits. That's what these two the two M boxes here represent, measurements. And note, by the way, that you're not doing the measurement on these 3 qubits. You're again doing entangling unitaries, taking this information out to 2 additional qubits. So using 2 additional ancillars, and you're doing measurement on these ancillars, right? Why? Because if I were to measure these 3 qubits, I would again break the superposition, right? I would break the coherence, because I would end up collapsed into one of these 2 states, and that again doesn't help my cause, right? Rather, what I need to know is to somehow identify which qubit the error occurred in, or identify the nature of the error in some way. And this correction is simply a unitary operation on these 3 qubits. For example, if it was a bit flip in the first qubit, then I simply need to apply a unitary, which is a Pauli X operator, on the first qubit, and I have reversed the bit flip, right? The key is to know where the error occurred, to what kind of error occurred, and that's what this measurement with additional ancillars helps me to do, right? Now, this process of measurement plus a unitary, involving again a larger Hilbert space, can essentially be represented as a completely positive trace preserving map, because that's also a kind of quantum evolution of the system, which is, if I again look at it from just the system point of view, it is non-unitary, right? And in fact, conversely, any trace preserving CP map I can represent via a unitary and a measurement in a larger space, right? So while this is a kind of nice picture of a decoder, a decoding map, which is just add additional qubits, do measurements, then do unitaries on your logical qubits, this is not the most general picture. The most general picture is that just as how the error was a CPTP map on the system Hilbert space, the recovery could also be a CPTP map on the space after the action of the noise, right? On the range of the noise map. Yeah.
Is there a question? So the recovery map is CPTP, right? But it will not recover into the pure state again, no? Where you are encoding the original qubit. No. Indeed, it will not. But the approximation to the original pure state.
That's right. So the idea is that so long as you can recover a state, so in fact, what you can show is if you have what's called a perfectly correcting code, a perfectly correctable code, then you can find a recovery map which brings you back to indeed the state that you started with up to a scalar factor, right? So, I mean, of course, finally you, okay, so let me back up here and show you this again. So if I were to look at it in this picture, where I have ancillar measurements and another unitary acting here, right? Although this says psi logical here, right, as if it were a pure state, actually what you're doing is you've added additional qubits and then you've traced them out, right? So indeed, this will not completely be a pure state. This will be a mixed state, but to a high degree of fidelity, you will get back the logical state that you started out with. That's the idea, right? So when one says, because you see there's a measurement process involved here, right? So automatically that makes this probabilistic. Automatically that makes this, that makes this process not a unitary process completely, but introduces this stochasticity or mixedness. So indeed, you will not end up with a pure state exactly. But if you approximate to the set of what are called correctable errors, so in this case, if I just think of the single qubit errors, right? Suppose if I say that my noise map only had single qubit noise operators, then I can come very close to being a pure state in this case. Okay.
Okay. So essentially, your code will have some kind of errors that you can completely correct, and some you can only correct up to some fidelity or some kind of.
Exactly. Yeah. Exactly. That's exactly right. So in this case, it's the single qubit errors that I will perfectly correct, and the higher qubit errors I cannot correct. Right? Yeah. Was there a question?
Yes. Sorry, Prabha. I completely confused myself. So basically, the bit flip error on alpha 0 plus beta 1 would be alpha 1 plus beta 0, something like that? Or,
yeah.
I mean, I understand the classical bit flip, but what's the guarantee that the bit flip is going to act exactly that way on a quantum superposition? I know it's a weird question, but
no, but that's the point, right? It acts in a probabilistic way, so you don't. So that's why this picture, right? That you start with. I mean, I could have started with a alpha 0 plus beta 1 instead of a 0. So this is the state after if the initial state will just get 0.
See here, what row you have written, I can interpret it as a statistical mixture.
Yes.
Because you have this. What you are showing on the next slide is a superposition. And
true, but again, I should really write a row which has basically the density matrix corresponding to this superposition, right? So there will be a density matrix corresponding to this superposition with all the off-diagonal elements, right?
Okay.
The alpha star, beta, the beta star, alpha, etc.
Yeah.
And indeed, it is again a stochastic mixture. It is again a mixture of identity and sigma x acting on that density matrix. Right? That's why I said the circuit picture kind of hides all that under the carpet, right? It pretends like there's the whole thing is, happening in a pure state fashion, but really it is not, right? Because, that's the point. You don't know whether it was identity or a bit flip, that at a given point in time, right, my bit is flipped with a certain probability, and I don't know what that is, really.
Okay.
Right?
Okay.
So that's what I mean by saying which bit was flipped, right? So it's as if I wait a certain time and there's a probabilistic process that has happened. One or more of these bits could have flipped, right? And I detect that by doing these measurements.
Okay, so...
But the underlying picture is one of density operators.
I see. So classically, basically, you take a vote of zero out of something like that. So this... entanglement is capturing some sort of a voting phenomena over here or something? Should I?
Yes. So these two C nodes. So I didn't want to go into the detail because I'm not sure but yeah, since you asked, then these two C nodes here, basically, so you start with the ancilla being 0. So if one of these two bits is flipped, then that will flip this, right? Similarly, if one of these two is flipped, that will flip this. So it's basically checking the parity of the first two qubits. This is checking the parity of the first and the third. And that's what's happening. Yeah.
All right.
So it's essentially a majority vote, exactly. But that's why then you have to again make this assumption that higher qubit errors are less likely than single qubit errors, because this parity check won't work if you also throw higher qubit errors in the mix, because then you will confuse different single qubit errors and the higher qubit errors.
Okay.
Right. Yeah. So the circuit picture kind of hides a lot of things under the carpet. It clarifies certain things in the sense that it tells you that there's a way of doing it using measurements and unitary operators, which is what we know how to do. But really, it's the CPTP picture that captures the essence of it, which is that the noise itself is a completely positive trace-preserving map, and the recovery in general could be a completely positive trace-preserving map. a measurement and a unitary is a special case of such a trace preserving map, right? I mean, at least this particular kind of decoding is a special case of this CPTP map.
Sorry, just one clarification. Can you go back to previous slide, please, once? Hello?
Prabha, where are you? So Prabha is apparently, okay, our audio is on. Hello, Prabha, are you there?
See, I also lost.
Sure,
okay,
yeah.
Great. Okay, so Sachin was asking you something.
Please go ahead.
I got it. Thank you. I'll ask later.
Okay, fine. So is this where I was, where I said perfect versus approximate?
You were just going for action of a channel E. So you should probably say anything below the recovery map. You should obviously again. Yeah.
Here, right? So this is where I was.
No.
Yeah,
In the
okay.
previous slide, but anyway.
No, actually before this.
Okay. Fine. Sorry, just give me a second. Yeah, okay. So here's where I was. No, I was just saying that this is an idealization, this idea of perfect correction, that you're able to somehow recover the state exactly after the action of the noise and recovery. But as Ayan pointed out, this is not always possible, right? And the best you can do is if you only restrict your channel to a set of correctable errors, then you might at best be able to get a scalar multiple of rho, right? But what happens in reality is you will always have errors which you cannot correct in a given channel for a given code. So you can hope to recover the state such that it's close enough to the initial state or the original state on the code space, right? And so this is the definition of an approximately correctable code, that every state in the code can be recovered to within some margin of error, right? To within some fidelity. What that means is there exists a recovery map, there exists a completely positive trace preserving map such that this is possible, right? So this is a sort of cartoon picture of what a perfectly correctable code should do. It should, the individual different Krauss operators, which is what I've called here E1, E2, E3, etc. Those are the Krauss operators that make up the noise channel. They should map the code space to non-overlapping parts of the Hilbert space, right? So each of this is a map on a two-dimensional space. So these different two-dimensional spaces that they get mapped to in some sense must be non-overlapping. That's when you can hope to have perfect correctability, because that's when you can hope to distinguish different errors and correct for them, right? But in general, what you're going to have is something which is, okay, so I should say that what also happens in this figure here is that these are exactly unitary transformations of the code space, right? And this is, for example, what happens in the case of the Pauli noise models, right? Where you have the individual noise operators or the individual cross operators themselves being unitary. So once I detect which error occurred, I can always reverse, because E1 itself is unitary, so E1 dagger completely reverses the effect of E1, E2 dagger reverses E2, etc. And furthermore, if they are non-overlapping, then in some sense, these operators are mutually orthogonal in some way. And so I can recover this information perfectly, right? But in general, so actually I wanted to put a more general figure here. Some of this is showed up. But in general, you could have non-unitary transforms of the code space. What is more, these different spaces will be overlapping in general. So neither will you be able to detect perfectly, nor will you be able to reverse perfectly, right? So that's the kind of feature of an approximate code. And I just want to give you an example of approximate code. But before that, I think I wanted to also tell you about stabilizer codes a little bit. So,
just one second. Yeah, for a spin-up system, it was easy to find out what are possible E. For a complicated system, is it possible to say what are possible E's are?
So that's exactly what I'm coming to, right? So you can have a continuum of different errors. Forget qubit, right? Let's say qubit, which is the question you're asking. Right? So I have a d-dimensional system. There could be different processes by which the information can decohere. There could be different kinds of noise channels that happen, right? But I don't really need to bother about these different kinds of noise processes if I have a unifying picture, which is what the Pauli noise channels do, right? So, I mean, of course, for qubits, they form a basis, but in general, I can think of a generalization of the Paulis for higher dimensions, right? And they still form a basis, right? So if I have a Q-trit, I can think of the corresponding shift and phase operators, right? And that again forms a basis in terms of which I can expand any other noise process, right? In terms of which I can describe any other noise process, right? So it's precisely for this reason that you could have different kinds of noise processes happening that you would like to see common ground, right? And so the way to do that is to discretize your errors in terms of some finite unitary set of errors, which is what we call an error basis. So was there a question? Okay.
Yeah.
I hope that, yeah.
Hello?
Yeah.
Ma'am, just one question. It may be little bit vague. So that, ma'am, the map you are using, I mean, those maps are, I mean, error is coming from due to the fact that the quantum capacity of that map is not one, right? Hello?
Quantum. What do you mean by which capacity? The quantum.
The map, I mean, the map through which the error is coming. So their quantum capacity is not one, right? So therefore, the error is coming into the quantum system.
Okay, that's one way of seeing it. Yeah.
So what I'm saying, ma'am, using quantum switch and using indefinite causal order, Chidi Bella and later the ISI group, they have shown that using two such quantum channels which has zero quantum capacity, you can make it to one. I mean, you can create a channel where you can do the perfect communication. So, ma'am, for that, if we can do it through quantum switch, why we need this error correction codes?
Okay, so I should tell you, yeah, I understood. Yeah, see, the capacity is a statement about the asymptotic transmission of information. It is not a statement about finite transmission of information.
No, but ma'am, what they have shown that for a single run, you can I mean, communicate the state. I mean, exactly.
I'm a little bit sorry to interrupt this. So, because we are running a little short of time. It's already 6:30. So
yeah,
I would rather say that these kind of questions, which are a little bit outside of the main thing of the talk, we could probably take at the end of the talk. Is it okay?
Yeah. Fine.
Yeah, and actually, I think we should discuss this more in the Quantum Information Journal Club. Anyway, yeah, but I mean, we'll talk about this later. Yeah. Okay, so if we discretize these errors in terms of a finite error basis, right, then it suffices for me to find error correcting codes for this set of errors, right, which is sigma, x, y, z, and identity. And of course, I can then think of an n qubit error correcting code where I encode the information from a single qubit to n qubits, right? And then these set of errors are simply taken from this Pauli group, right? The n qubit Pauli group. The set of errors is simply tensor products of the form x, identity, z, y, etc., right? In particular, because of the linearity, I mean, I have not touched upon error correction conditions here and so on, but one can frame this idea of, non-overlapping subspaces, which I showed in the previous picture, in an algebraic way. And that's what's called an error correction conditions. So since these error correction conditions are also linear, your system evolution is linear. So it suffices if I can correct for X noise and Z noise, because Y is a combination of X and Z. So if I can correct for independent X noise and independent Z noise on each qubit, then I'm done, right? So that's where this whole formalism of stabilizer codes comes in, right? That it suffices for me to look at the n qubit Pauli group, right? The Pauli operator basis for n, for C2 tensor n, right? If it suffices for me to look at that as my set of errors, I consider an abelian subgroup of this. This group is, of course, non-abelian. I consider an abelian subgroup of this such that it does not have minus I as an element. right? And then I look for states that are stabilized by this abelian subgroup. Okay, so what do I mean by stabilized? I say that a vector is stabilized by an operator if it is left invariant by that operator, that it's a +1 eigenstate of that operator. Now, the set of all +1 eigenstates of such an abelian subgroup naturally forms a space, and indeed it forms a, one can think of it as a code space, right? And that's what stabilizer codes are, right? So you define a space which is a set of all vectors which are stabilized by the operators in this abelian subgroup of the Pauli group, right? And this indeed forms a linear vector space. And the question is, can one use this as a code space? It's easy to find out what should be the dimension of such a linear vector space, right? Because if this subgroup has R generators, and I am talking about a 2 to the n dimensional Hilbert space, 2 to the n dimensional space, then the code space will be a 2 to the n minus R dimensional space. And that's easy to show, right? So this sort of picture is what gives us stabilizer codes, right? So just a little bit more about stabilizer codes. So I already said this. Yeah. So now one can, okay, so let me just back up a little bit. So the reason I wanted an abelian subgroup of the Pauli group is the following statement, right? One can look at the normalizer of this group S. Remember, S is the script S is an abelian subgroup of the Pauli group. I can look at the normalizer of this group, which is basically the set of all operators in the Pauli group which commute with S, right? Now these would be my undetectable errors, right? And any error which is not in the normalizer would anti-commute with the stabilizer operators, and therefore these would be detectable by the code. Why so? Because they will no longer belong to this set of states that are stabilized. They will take your code space necessarily to something which is outside, and in fact you can show that this in fact takes it to something which is orthogonal to the code space. So any operator which does not commute with the stabilizer, with the elements of the stabilizer, or in particular the generators of the stabilizer group, right, is a detectable error. And because your set of errors is from one of the Paulis, which are all reversible, it's also a correctable error, right? So one can recast this notion of error correctability in terms of Pauli operators that are inside the normalizer versus outside the normalizer of the stabilizer group, right? So this is probably as much as I wanted to say about stabilizer groups, because the aim of the talk was to talk about Petz map and such, but I just wanted to mention this notion of stabilizers and so on, because that's something one often finds used in the literature. So this 3-qubit bit flip code is the simplest example of a stabilizer code, because this two operators, the ket00, ket111, and linear combinations of 0001111 are in fact stabilized by this set of 4 Pauli operators, right? So you will find that the single qubit X operators don't feature in this, obviously. What is more, they are indeed operators that anti-commute with these operators, right? A single X anywhere, XII, IXI, etc. They all anti-commute with these stabilizer generators. However, sorry, was there a question? Okay, somebody's mic has to be muted.
It was just a bit flip error.
So, but if I have a 2-bit flip error, right, which is probably what just happened, which is you have XXI, right, then you see that it commutes with the second stabilizer generator, right? And so that is something which cannot be detected by this code. It's something which cannot be corrected by this code, right? So you can sort of build on this idea, and you can construct stabilizer codes of various dimensions and so on. You can still construct codes beyond qubits, because you can think of, like I said, generalize the Pauli operators to higher dimensions and think of stabilizer codes on qubits, etc. And this leads to something called the Hamming bound, which says that the shortest perfect error correcting code requires 5 qubits to protect a single qubit, right? This again comes from the fact that
How is that a group? I don't see closure. I don't see closure. If I take the second and third and multiply, I don't get. Or it should be IZZ, the last guy.
Oh, sorry, this should be IZZ. Yeah.
Okay,
Actually,
sorry.
just 2 of these is sufficient to generate the group. I needn't have written all 3, just 2 of them. Yeah, sorry, this shouldn't be here. Yeah. It should be IZZ. Yeah, thanks. There's just 2 generators actually. Okay, so this discretization then gives you bounds on the dimension of the code space you need to correct, a certain number of errors. Yeah.
If you want 1-bit flip, then shouldn't you have just XII as a generator of the error? So
these are not the generators of the error. These are the generators of the code space, right? So these are the operators whose eigenstates forms the code space. So in fact, that's precisely the point actually. You don't want the detectable errors to feature in the stabilizer group. You want operators here which will not commute with the errors, so that the errors have a non-trivial action on the eigenspace of this group, and then they can be detected.
Yeah, so your earlier statement about the other operator which these anti-commute with was that it is anti-commutes with XII. Is that right?
Yeah.
So that's for this modification.
Yeah. Because it's basically these are parity things, right? So there should be 2 Z's here, basically. So this was an error. This should be IZZ. This was my own bit flip error. This should be IZZ, right? So each stabilizer operator here will have 2 Z operators. So it will always anti-commute with a single X error.
Okay.
Yeah. That's the basic philosophy of this. And that's how you can design codes, sort of higher dimension codes and so on. But note that this code, which is stabilized by, say, Zi, so ignore this third operator for a moment, but just think of Ziz, Zzi, the product of that should anyway give you the third operator. But this kind of a code will not correct bit flip, phase flip errors, right? Because they all commute with your stabilizer generators. The IIZ commutes with the stabilizer. So those are all in the normalizer of this group, right? So it will not correct single phase flip. So if you want to take this idea of a bit flip code, the same redundancy thing, and extend it to also correct for phase flip, then you get the Shor code, which is 9 qubits, right? So
okay, so we lost Prabha again.
Come up to this point then, okay? I'll kind of skip a few slides also. I'm sorry. See, the thing is, because of the audience, I was not sure where to pitch it, and I'm sorry.
No. Actually, we are all. That was very helpful. All the things that you're doing. So you should not think of changing your plan of action or anything. Just do that. It's better to just simply have a part 2, simply because it is. Yeah.
Okay, so let me proceed. So I just told you that if you were to do this, what I call general purpose error correction, which is that you discretize your errors in terms of Pauli's, and then you look for positive eigenvalue, eigen subspaces of certain abelian subgroups of the Pauli group, right? And that forms a natural error correcting code for Pauli errors, right? Or any channel that can be broken down into Pauli errors. But if I don't want to break down my channel into Pauli errors, I want to look at the noise map in itself, like the amplitude damping noise, for example, which had E0 and E1, then it turns out that I can actually identify shorter error correcting codes. So I don't need this 5 qubits to do a single qubit worth of error correction if I'm willing to sacrifice the general purpose nature of the code and stick to correcting specific noise. Well, that's what we did with the 3 qubit code. We just corrected for bit flip noise alone, but we couldn't correct for phase flip or the Y kind of noise, right? So similarly, here's an example of a 4 qubit code which corrects for single qubit amplitude damping errors, right? And in this case, this is the picture that I showed you earlier, where your code space gets mapped to mutually orthogonal subspaces but they are not necessarily unitary transforms of the code space, right? And this was the inherent non-unitary nature of the amplitude damping channel itself, right? So what you're doing out here is you've identified a pair of states which have a certain parity, if you notice in the bits, right? They're all even parity. You have all zeros, all ones, 2 zeros and 2 ones. You have identified states which still get mapped to orthogonal parts of the Hilbert space, but they are not necessarily unitary transforms. So you're willing to take a bit of a hit in that, but you have encoded into something shorter, which from a resource point of view is more useful, right? So much more recent examples of these kind of codes, the so-called CAT codes, which are being used, the so-called GKP codes, the Gottesman, Kitaev-Preskill codes, binomial codes. They're all examples of channel-adapted codes in the sense that they are tailored to specific noise processes or specific noise models. They take into account some structure or symmetry of this noise and do not go down the stabilizer route of finding codes, right? So what is the hit that we're taking? We're taking a hit in fidelity, right? So how do I now compare? So I have the 5-qubit stabilizer code and I have this 4-qubit code. How do I say if they are equally good or one is better than the other? So I use this metric, which is a metric on the space of operators on the Hilbert space. So it's a trace of square root of rho to the half sigma rho to the half. This is called the Bjor's metric or some form of the Bjor's metric. If I assume that I always start with a pure state, right, then this rho simply becomes psi, and then and then this fidelity function becomes simply square root of the overlap of the initial state with the final state, because the initial state was a pure state. So I can get rid of the square root also if I define f squared as my measure of choice, which is what I have done in my work. I've taken this f squared measure, right? And then now I want a guarantee that this fidelity is going to be high for all states in the code space. So this is what I mean by a worst case fidelity, that under the action of a noise and recovery. So you notice that the left-hand side makes no reference to a state, right? Because I have basically minimized now over all states in the code space. I'm saying that if this fidelity is high, which is this f min, which is the worst case fidelity, then if that is high, then I'm guaranteed that any state is going to be able to recover. You're going to be able to recover any state with high enough fidelity, right? So that's what this worst case fidelity measure does. It minimizes psi. It minimizes over all states in the code space, this overlap function, basically, this fidelity function, right? And it turns out that it's sufficient to minimize over pure states because this measure is jointly concave in its arguments. So those are all properties, some nice properties of this measure. So now if we try to compare for this amplitude damping noise, 4, 1, this notation just means that I'm encoding 1 qubit in 4, right? So this achieves a worst case fidelity of 1 minus something order gamma squared, where gamma is the decay probability, if you remember, the probability of the excited state decaying to the ground state. You compare with the so-called perfect 5-qubit code, which is a stabilizer code, encoding 1 qubit into 5, then you find that the worst case fidelity is pretty much similar to that of the 4-1 code, right? So channel adapted error correction may actually do comparably well, or sometimes even better than general purpose error correction. Although, of course, you can only correct for a specific noise process in that case, right? So this is a shorter code of comparable fidelity. So let me now move on to talking about channel adapted error correction, and I'm inching close to the Petz map now. So we say that, so this definition was already there, except I've formalized it now in terms of this measure, the worst case fidelity measure, right? So I only now have reference to a code space, the noise and the recovery. The dependence on states is removed because I've minimized over all states in the code space, right? So if I were to now try to identify for a given noise, what is a good code space and what's a good recovery map, right? This is a triple optimization problem because I have to find the best code and the best recovery, which gives me a good worst case fidelity, right? So it's a triple optimization over code spaces, over recovery maps and states. And finding the recovery map, so let's say that I fix a code even, right? So let's say I give you a code space, right? So that I get rid of one of these optimizations. It's still a double optimization. And this by itself does not have nice convexity properties. If you change the fidelity measure, then you can recast this as a convex optimization problem. You can do what's called semi-definite programming, etc. But if you were to simply do this for the worst case fidelity measure, which physically seems to be a good measure to use, then this has no structure, this optimization. It's a hard optimization problem, right? Because this function is not linear in its arguments, so it's a computationally hard problem. So there are various workarounds for this, right? When people started looking at this idea of channel adapted recoveries, which means for a given noise, I'm asking what is the best recovery map, right? Then, of course, there are relaxations you can do to make this a semi-definite program. You can change the fidelity measure and make it what is called entanglement fidelity. Then also this becomes tractable via semi-definite programs. But what we were interested in, and this is where my work comes in, is we wanted to address this question analytically. So can I construct analytically a recovery map, which is guaranteed to give me good recovery for any given noise channel and a code, right? And we drew inspiration from this paper, which, by the way, a lot of recent people have also drawn inspiration from. This is a seminal paper by Barnum and Knill. The paper is titled Reversing Quantum Dynamics something. And they come up with this idea of a pretty good analytical recovery map, right? The measure of fidelity they use is this average entanglement fidelity, which I mentioned here. I'll define it in the next part of my talk when I actually get into the holographic stuff, because that's what people are using there these days. But let me just conclude by defining this channel adapted recovery map, this pretty good recovery map. So the idea is you take the noise channel, you pick any code space, right? Which means I define some, I mean, if it's a single qubit, then I may take a 4-qubit space and pick 2 orthogonal vectors in the 4-qubit space. I may take a 5-qubit space and pick 2 orthogonal vectors. So that's sort of up to me, right? But for any choice of code space and noise channel, I can define this map, right? Which is called the so-called Petz map. This is a map with Krauss operators, which are given by this expression out here. So maybe I have this explanation. So I don't mention what P is. Okay, so I should mention here that P is a projector on the code space, right? P is basically, you can think of this as the identity operator on the code space. In the case of 3-qubit code, it's just 000 operator 000 plus a projection on 111, right? That would be the projector on the code space. So the Petz map is basically defined using Krauss operators, which have this form. So you see that the adjoint of the channel operator features here, right, in the middle. So what I have in the middle here is EI dagger, right, where EI are the Krauss operators of the noise. But recall I told you that if I were to just define a map with EI dagger as its Krauss operators, that is not always guaranteed to be trace non-increasing. It is guaranteed to be trace preserving if and only if the map is unitary. The noise channel itself is unitary. So that's what makes the Petz map definition more complex and more interesting. It is in essence the adjoint of the map, of the noise map, right? If the noise map were purely composed of unitary operators, if these were all UIs, like the Pauli noise, then you're done. The Petz map is simply PEI dagger. But because you do not have unital channels all the time, you have to add other things to make this a trace preserving or trace non-increasing map. This other things that you have to add is basically this pseudo inverse out here. This is basically, you take the projector on the code space, you add the noise on it, and you take the pseudo inverse of that operator, right? So it's the action of the noise on the code space. In some sense, it's a kind of average operator, right? It's capturing the range of your noise map, if you will. And then you're taking this inverse on the range, right? Which is fine because that's where you want your recovery map to operate. You don't care about the null space of E of P. You only care about the support of E of P.
There's a square root there.
So it's to the minus half. Yeah. The reason for the square root is that what you're asking?
Yes.
The reason for the square root is to normalize the map, right? So let me just go down and say this, the very last point here. So you can think of the Petz map as composed of 3 separate CP maps. One is the adjoint map. Like I said, the adjoint map is CP, but not TP in general. But what comes before that is this normalization map, which you can think of as the single Krauss operator map of this form. E of p to the minus half, E of p to the minus half, right? You take the pseudo inverse on the range and you take its square root, right? And you will see that this makes sure that this Ri dagger Ri sums to identity, right? So if you take Ri dagger Ri, you will see that you'll end up with 2 copies of E of p to the minus half. What will be sandwiched in the middle is E of p, and so together they will give you identity on the code space, right? Okay, so these are the properties of this map. You can show that this map is exactly the same as the perfect recovery map if you had a perfect error correcting code, which is, like I said, if you had a Pauli channel, if you had the bit flip channel, then this is simply a projector on the code space. Before that, you're just doing the sigma x operation, right? Because the E of p would just be identity in that case, because that map is unital, right? So this part becomes non-trivial only in the case of a non-unital map, right? And that's when you need this part to make this trace preserve, right? The key point is we show that this map is a near optimal recovery map. And this was the same result of Barnum and Kinnell, except they showed this for the average entanglement fidelity, and we show this for the worst case fidelity. And the details of the statement, maybe that's where I'll start with next time, that if I have an optimal recovery map for this combination of noise and code, then the Petz map will achieve a worst case fidelity, which is always close to that optimal recovery, right? Or I pick any recovery map for this combination of noise and code, the Petz map will always achieve a worst case fidelity, which is close to that, right? In particular, it will achieve a fidelity that is close to the optimal recovery, right? So and this part, last part probably doesn't apply because I didn't really talk about error correction conditions and stuff, but one can also rewrite the error correction conditions purely in terms of the Petz map, right? So let me stop here. I should say that this is one form of defining the Petz map. And what I'll do next time is you'll see that there are multiple variants of the Petz map, different ways of defining the Petz map. But the fundamental idea is the same, that you have these 3 maps, right? 3 CP maps, one part which normalizes, which we call a normalization map, but essentially that's what it's doing. It's making sure that this complete map is trace preserving. Then there is an adjoint piece, and then there is a projection onto the code space. In cases where you don't have a code space, but you're talking about a single state, then it's just a projection onto a single state. If you're talking about an ensemble of states, which is not a code space, but just some ensemble of states, then this could be a projection onto that ensemble of states, right? Okay, so maybe I will stop here. Questions?
Okay, Prabha, that is great. We should continue. But although I should probably give opportunity to others to ask questions, but I have an immediate question here actually. So the immediate question is that you're doing this minimization in some sequence, right? I think, so you're probably minimizing over the recovery map at the end, and you get this Petz map as a result, so that gives you the best or worst case fidelity. But then suppose if I would have minimized over the recovery channel, suppose I take the recovery channel up first, and then I want to minimize over the code space. So can I do it? Can I understand it from the Petz map, what that should do? I don't know.
Yeah, that's a very nice question. That's a very nice question. See, but I must tell you that, first of all, maybe I didn't explain this properly. So I spoke about numerical optimization on the previous slide, right? And there, indeed, this order can make a difference, right? Whether I first pick a code and ask what is the best recovery map, or I first pick a recovery and ask what's the best code, right? If you use a so-called nicer measure, like this average entanglement fidelity, then it turns out that both the problems are convex optimization problems. And in fact, you can actually do them, and it turns out, in fact, that one is dual to the other in some way, right? If you know about this semi-definite programming duality kind of thing, right? Convex optimization duality. So it turns out that one optimization is a dual of the other. There's the state operator duality in play. So this actually becomes, interesting in this case, where you can actually fix the code first find the optimal numerical recovery, then iterate. So fix that recovery, find the optimal code, and so on, right? So you can kind of do this in a iterative fashion that actually converges, right? So that's what this paper of Peter Shore and the student, that's what they do, right? But what I'm talking about as far as the Petz map goes is I'm not really fixing anything, right? It's not like I picked this code space as some optimal code space or something. I'm saying you pick any old code space and you pick any old noise channel, right? What the Petz map will do is it will achieve a fidelity, a worst case fidelity, which is close to that of the optimal recovery map. So whatever is the best recovery you can do for this combination of code and noise, the Petz map will always come epsilon close to that. That's the sort of precise statement, right? And this holds for any Petz map, the Petz map that they're now using in holography, the variants, all the variants of the Petz map, right? They all satisfy this near optimality property.
How does one prove this? It looks very open.
Yeah, so in the next slide, I have the actual statement of this. So as you can see, this is the precise statement of optimality. It's actually just a few steps of algebra, Okay, so one nice thing to note about the Petz map is because of the way it's constructed, that it has this piece of this EI dagger E of P to the minus half, right? So when I compose these two maps, the noise and the Petz map, I end up with a unital map, actually. So that is one nice feature which helps you prove this kind of optimality. But it's basically, at least as far as this worst case fidelity measure goes, it's a kind of Cauchy-Schwarz statement finally. In some sense, you're breaking up the fidelity into two parts. And you can do that because of this feature that this has the adjoint of the map sitting here. Actually, even the Barnum-Knill statement you can see fundamentally coming from a kind of Cauchy-Schwarz kind of statement.
Okay.
Both, whichever measure of fidelity you use, you can break it up into two parts because the Krauss operators are simply, up to this factor, they're simply EI dagger, right? So that's the key thing here. Yeah. Yeah, actually, the harder thing is how they, the information theoretic implications, which was my next part. I was going to talk about relative entropy and all that stuff. I realized I was too ambitious, but anyway, yeah, that's where it actually becomes even harder.
No,
that's where you really.
We are very happy. You should be ambitious. It's just that you need a second talk. Yeah, it's thankfully you're ambitious, so that's nice.
Sure. Very good. Sure. Yeah. Yeah, no, I'm happy to do a second half as well. But yeah, any other questions?
Can I ask a quick question, Prabha?
Sure, Bala. Yeah.
Yeah. So is this Petz map, the construction you made, specific to the fact that you've chosen to look at the distance between two states through the fidelity?
Yeah, indeed, that is true. Actually, that is true. Like I said, there are different variants of this Petz map. So the earlier version, which was used by Barnum and Knill, where they used what's called the entanglement fidelity as a measure, turns out that there you have to use some kind of average state on the code space. Okay. So here we defined it using simply the projector on the code space, right? So there you have to actually take a maximally mixed state on the code space instead of the projector. And that's what gives you the near optimality, right? Now you could use a different measure of closeness, by the way, which is what's called the relative entropy, right? That's also a measure of closeness. Right. So then you would have a state-specific Petz map, actually. Okay. So yeah, indeed, what the choice is to that extent governed by the measure of choice. Yeah.
Okay. Thank you.
Yeah. Okay. No other questions?
I
had an sorry. Yeah, please go.
Right. I don't know if that was just asked, but my question is that, can you perhaps summarize for us what the use of the Petz map is in holography?
Okay, so a two-line summary would be the following, right? You view this holographic correspondence itself as a kind of quantum error correcting code, right? You view this correspondence as an encoding from the bulk to the boundary.
Right.
Right? And so the question then becomes, how do you reconstruct the bulk, given that you have only limited access to some sub-region? So that's what this whole entanglement wedge reconstruction is, as I understand, right? I'm, of course, not the expert on this, but this is what I understand, that you take a certain region of the bulk, governed by some other considerations, like some kind of extremal property of the entanglement entropy and so on. So if you have some part of the boundary and you are given access only to a sub-region of the bulk, then how can you reconstruct the state, right? At the boundary. Yeah, and that's exactly what. So what has been shown is that a certain variant of the Petz map is what you need to construct there. Of course, now it's a Petz map not on just states, but actually it's a Petz map defined for an operator algebra. Right? It's a Petz map defined for the algebra of observables on the bulk. And basically an extension, I mean, that was the result I was going to talk about, which is an extension of this Barnum-Knill result, which I just mentioned, for operator algebras. Right? And then you can show that in trace norm, you can actually recover the state in the region of interest, which is this entanglement wedge region, right?
And so, I mean, we want to recover the bulk state from the boundary, right?
Yeah.
So the Petz map acts on this operator algebra, which is defined on the boundary, right?
That's right. That's right. Yeah.
Right.
Yeah.
Okay.
Yeah.
And now, see, I thought the Petz map was something special. Like, I mean, it is nice, but I mean, from what you have described, it just seems like the most sort of general way to do approximate error correction.
That's exactly what I thought as well when I wrote that paper. Yeah.
Right. So when they're talking about the Petz map and all that, I mean, they're just saying, okay, well, we are doing approximate error correction in the best way we know how to do.
Correct. However, the devil is in the details, as they say, right? So what is the appropriate Petz map to use for a given situation, right? First of all, within the domain of finite dimensional spaces itself, there are 2-3 variants of the Petz map, depending on what measure you want to use, etc. And also, as Suresh was saying, proving this near optimality statement is not trivial, right? And that's why these results are interesting. The fact that, okay, you can always give me a Petz map, but what's the guarantee that the Petz map is going to do well in that scenario, right? The fact that on an operator algebra, you can construct such a map and that it gives you, in fact, the most recent statement is that it can give you something which is close in one norm or trace norm, right? Which is an important metric. I would say something like relative entropy is a more indirect measure, if you will, but something like a one norm is a direct distance measure, right? And the fact that this Petz map gives you that is what is interesting, right? So, yeah, I mean, that, I think it's non-trivial to actually prove these near optimality statements.
Okay.
Just a comment, Prabha, actually, regarding this fidelity that you are using, I think Devjyoti is here in the audience.
Yeah.
Has worked on it in quantum field theories, and one can show it. It's related to correlation function. So one can, in some, at least if you are like perturbation around the vacuum, and if you're not too far away, so you're very small excitations on the vacuum, then you can actually reduce this measure to some correlation function. So maybe the version that you have already presented some use already in the context of holography.
Actually, that was my, going to be in the end. I had said that is one of the things I'd actually now like to look at, having now spent some time understanding the various Petz maps that are in play. I find that so far people have used either relative entropy, actually it is the, the monotonicity of relative entropy as a kind of measure, or the one norm, right, which is this Shen and Pennington result. But no one has really used this worst case kind of measure, So actually, if that can be done, and if we can simply use this version, which is to me the simplest version of the Petz map in some sense, can be used. Because the first paper which used it had this twirled Petz map, which is too many bells and whistles on top of the Petz map and so on, right? So, but if this can be used and we can show something, that'd be very interesting. Actually, I don't see such a statement as far as I know. So, Yeah, and my claim, I think that the scaling also would be better, right? In the sense, so what is the, by scaling, I mean, if your optimal recovery map can recover with some, up to some delta error, then typically the PETS map, the way we define it, we show that you can actually recover up to order delta itself with a factor which depends on the dimension of the code space. But the results that are there in the literature, whether with respect to the relative entropy or with respect to the one norm, they all go off to a square root of delta. So it actually doesn't scale that well compared to what the worst case fidelity scaling you can do with this kind of a PETS map. So that would be interesting. I think to see this translated into the ADS CFT context would be very interesting, actually. Yeah.
Okay, I think it has been a very long discussion and very, very interesting, but we should simply continue at the end of this month or maybe next week, depending on whichever is earlier available slot.
Mm-hmm.
So thanks for giving your time and being so ambitious, and thanks everybody else for attending.
Thank you for being a good audience. I guess.
Can I just add that, for what it's worth, I would be really interested in hearing the rest of your presentation. So if you do.
Okay.
Oh, great. Okay. So you already have a confirmed audience. Yeah. Okay. All right. So have a nice evening, everybody. And it's time to say goodbye.
Yeah. Thanks for staying back, guys. Yeah. Thank you. Yeah. See you all. Yeah. Bye.